Now we're looking at few concepts which are important. So we're going to look at span, basis, and dimension, which some important definitions for a vector space. First, let's look at span. Okay. Let's start. Span. Span is write this as a definition first, then we'll look at the mathematical definition. Span is the set of all possible linear combinations of set of vectors v1, v2, etc. V. This is a set of vectors, and the set of vectors is known as the spanning set. So what does this mean? This is actually just extending the idea of linear combinations. So earlier we looked at vectors v1, v2, etc., vn. We said y is a linear combination of these vectors can be written as sigma I is equal to 1 to n ci vi, where ci belong to field left. Both these cases I varying from 1. So, etc. And this is how we've defined. It's not I belong to, so I is equal to. This is how we have defined linear combination. So what does span say? Span of v1, v2, etc. vn is the set of all y belonging to Rm such that y is equal to sigma y equal to 1 to n vi vi, where ci belong to. This is the definition of span of a set of vectors. These vectors are called as a spanning set. The immediate consequences, the immediate thing which we are expected to see is, okay, for proofs, for this course, I'll be using green ink. So let's say we have a statement. Question. Prove. What should we prove? That span of v1, v2, etc., vn is a vector space. We should prove this. How do we prove this? Let's try to prove this. Okay, let's try to prove this. So there are two things we have to prove for vector spaces, right? One is it's closed under addition and closed under subtraction. Okay. So let us say that there be A and B such that A is the linear combination of these vectors in terms of some linear combination, some scalar alpha is, set of scalars alpha is. vi, and B is another linear combination of same set of vectors with another set of scalar beta. So both these vectors are actually spanned by the same set of vectors v1. Both a comma b belong to the span of v1, v2, etc. vn. We have to prove one a plus b belong to the span of v1, v2, etc. vn. Second thing, what we have to prove is some lambda times a belongs to the span of v1, etc. vn. Let's try to prove one. For one, what is a plus b? A plus b is sigma I is equal to 1 to n alpha I vi plus sigma I is equal to 1 to n beta I vi. Okay. So vi's are actually the common terms. And what sort of property are we trying to use here? Associative property? Yes. So we can just write that as sigma I is equal to 1 to n alpha I plus beta I times vi. This we can actually call it as some gamma I times vi. This is again, this belongs to the span of v1, v2, etc. Again, this is proved. Now let's look at 2. Let's say lambda times a is equal to lambda times sigma I is equal to 1 to n alpha I vi, which in turn is sigma 1 to n lambda times alpha I vi. This we can call it as some delta. Please. So this again belongs to the span of vectors v1, v2, etc. vn. So both these properties are satisfied. Hence, okay, span of vn is a vector space. It's a very simple span of vectors v1, v1, v2, etc. vn is a vector space. A few more things which we can look into. This will actually help. Let's say we have vectors v1, v2. Okay, the proof is over. Okay. A few more ideas which we would like to explore. One is, see, we have vectors v1, v2, etc. vn. We've already seen that we can stack these vectors as columns of a matrix v2, v3, etc. vn. We stack these matrices as columns of matrix. What will be the dimension of this matrix? It is A belongs to R m cross n, where each vi is an m-dimensional vector where I varies from 1 to etc. Now, we can, instead of writing the span A, we can also write this as the range space of A. range space of A, or it's also known as the column space of A. How do you define this space? It's actually the set of all y's belonging to Rm such that y is equal to A into C. As C belongs to R and I reckon this is another way of saying what we have seen here. Here, we have expressed y as a linear combination of all these vectors, set of all linear combinations, right? Yeah. Similarly, here, if we take A into C, one set of C, we get a y vector. Similarly, if we take all such C's, then we get a set of y's. Then this is again what we call as the span of vectors, these vectors. Another way of calling this is this is as a range space of A, or the column space of A. This is again a vector space. Again, a vector space. Can I prove it? Yeah. Not difficult to prove. No, I'm not actually trying to prove it now. So we've seen the concept of span. We've seen how do you express that in terms of vectors. Seen that span of vectors is a vector space. We've also seen range space of A. If we stack these vectors as columns of a matrix, we can express a span as a matrix multiplication between this matrix and the corresponding with any vector C. Okay, C being the linear combinations of these vectors. This is actually let's get reminded that this is right multiplied. A is on the left side and C is on the right side. If C is on the left side and you're left multiplying it, it has another set of implication. So right, like in terms of stacking these matrices, I mean stacking these vectors along the rows of a matrix. It's in the order. Okay, the idea is actually similar. Now let's move to the next topic, which is basis. Basis. So we've seen span, right? Span of a set of vectors. And we've seen that these vectors are known as spanning set of a vector space because they indeed form a vector space. Now, let's look at what a basis is. Let's write the formal definition. A set of vectors v1, etc., vk. Know that we're writing vk, not the same vn as earlier, is said to be a basis of a vector space V if this is a set which is both linearly independent and spanning set of V. This is the definition in English. Now let's try it mathematically. So base, I mean the set of vectors Vk is basis if. Is it if and if or if and only if? Okay, it's a definition. So Yeah, let's just write if you know it doesn't have much. How we define. First thing is they have to be linearly independent. What does that mean? Sigma I is equal to 1 to k ci vi is equal to 0 implies C1 is equal to C2 is equal to Ck is equal to 0. Next thing is it's a spanning set. So span V1, V2, etc. Vk, which is sigma. Okay, let's call this as okay 1 to n. Now let's call this as the set of all y's, right? This is a set of all y's, which that y belongs to such that sigma I is equal to 1 to k vi vi. This is actually the span, which is equal to the vector space. Both these conditions are satisfied, like 1 and 2. We call this as a basis. So another way of saying a basis is, so before that, let's see here, what is the significance of this? Here it's Vk, and here it's Vn. So both Vk and Vn can span a basis, but if it has to be, sorry, span a vector space, but if it has to be a basis, then it has to be linearly independent. Uh, so what can we comment about k and n? Is k equal to n, or k greater than n, or k less than n? Oh, how is it going to be? Okay. So it turns out that k is actually less than n, less than or equal to n. If you have given a set of vectors which spans a particular vector space, the basis could be actually equal to it or less than it, but not more than that. So another way of actually defining basis is the basis is the minimal spanning set of a vector space, or it is the maximal independent set of that vector space. So this is actually pretty clear, I think, the argument which you have made earlier. What does maximal independent set mean? So we have to span a vector space, let's say Rn. How many vectors do we need? Linearly independent vectors do we need to span the space? Take one, so it has no question of linear independence, just one, so there's no question of independence. Here, let's say we have two vectors, v1 and v2. Can we span the entire 3D space? No. We only span the space, the plane with these two vectors, even if they're linearly independent. We need another vector which is linearly independent of both of these vectors to actually span the third dimension. So what does that mean? This is the maximum possible set of linearly independent vectors which can actually span the vector space which you're trying to represent. In our case, this is R3. Okay, so this is the idea of maximal independent set. Okay. So there are some properties which is actually uh, properties of basis, which we can look at now. Let's say, okay, and properties of basis. First thing is that a basis is non-unique. So there could be multiple bases for the same vector space. So it's not unique. But if you take a basis, if you fix a basis, every V belonging to a vector space can be uniquely represented as linear combination of the bases. What does this mean? We can choose multiple vectors, let's say v1, v2, etc. vk. This can actually be the basis of a vector space. Similarly, we can have another set of vectors, call it z1, z2, etc. zk. The another basis, basis 1, basis 2. So both these need not be the same. These v1 need not be equal to z1, or any of these vectors could be entirely different vectors, set of vectors. So basis 1 is not same as basis 2. So also there's something which is interesting here. We've taken the same number of vectors. Here we have k, here we have k. What is it necessary to have the same number of vectors to span the basis? This is something which we'll discuss later as what we call as basis theorem. Turns out that both has to be same. Okay. But this is not unique. So the basis of a vector space is not unique. What about the representations? So what do you mean by that? For example, a vector, let's say a vector, let's say x, belong to vector space V, right? X can be expressed in terms of linear combinations of this basis 1, as alpha I vi. Similarly, X can be also expressed as linear combinations of the basis 2, like beta I ci. V1, V2, sorry, Vi, set of all Vi's and set of all Zi's need not be the same, need not be unique. There could be another set which is different from V, a set of Vi's and set of Ci's. And but if you fix this set of Vi's, then X has a unique representation. So X is equal to sigma I is equal to 1 to n alpha I Vi, and X is equal to another set in a combination of beta I Vi for the same X and for the same basis. Alpha I should be equal to beta I. So this would be unique. But if you change the basis, the representation need not be unique. And you have another vector, let's say Y, which is again a linear combination of these, say gamma, Vi. This is different. X and Y, gammas are not, gammas need not be equal to alpha i's. But a single vector has a unique representation. Okay. So this can be used as a way to represent vectors if you fix a set of bases. So okay, I think that is understood. Another important property is every vector space has a basis. Another interesting definition we can actually look into or is actually something known as dimension. Okay, then we'll look into the concept of dimension a little later. We discuss the basis here. So let's take a statement here. A vector space V is finite dimensional if there exists finite set of vectors V, which is a basis of V. What does it mean? So let's say a set of vectors Vn is the basis of a vector space V. If, okay, let's say this is there, and this vector space V is finite if it's finite dimensional if n is less than infinite. Okay, that's what we meant there. So if n is equal to infinity, then it is infinite dimensional. Okay. We have seen span, we have seen basis. Now the concept which we have to see is what is known as dimension of a vector space. Seen span of a vector space, we have seen basis of a vector space. Now we have to look into what is known as the dimension of a vector space. So to define dimension of a vector space, we have to state something which is known as the basis theorem. We have discussed this loosely in the previous section. Let's discuss this in more detail now. What does basis theorem say? Let's look at basis theorem. Okay, let's put this in green. That's what we are thinking earlier. Okay, can we get a darker green? Maybe difficult. Okay. Look at this green. So what does basis theorem say? Oh, sorry. If some basis of a vector space has finite number of elements, then all bases have same number of elements. And this number of elements in the basis is called dimension of a vector space. Like, how do you write this more precisely? Let us say spanning set V1, V2, etc. Vk is the basis of a vector space V. Then dimension of vector space V, yes. Okay, I don't know where we have to use curly braces. Let's use square brackets. Sorry, circular brackets. V is actually k, which is the number of vectors in the basis. Okay, and basis theorem says if we have another spanning set W1, W2, etc. Wn, or let's put it like WL, be also a basis of V, because basis can't be unique. Need not be unique. What basis theorem says is dimension of V, K is equal to L. This is what basis theorem says. Okay, how do we prove this? Let's look at the proof. Proof. So this is kind of proving it by contradiction. So let's write this down. Proof is by contradiction. Say we have set of vectors Vn and W1, etc. up to W2, etc. up to Wm. So these two are two bases of vector space V. Without loss of generality, we're assuming, initially we're assuming n is less than or equal to m. So what we do first, we can replace one of the vectors Wi by Vi and still have a basis for V. Why this is true? Why? Okay, let's look at why. Why is it so? We suppose Vi is one of the vectors of the basis. Okay? In Vi can be actually expressed as alpha 1 W1 plus alpha 2 W2 plus etc. plus alpha n Wm. Why is it so? Because it is a basis. So it spans V. So any vector can be expressed as a linear combination of the basis, right? Not be, yeah, it'll be exactly a basis. It just need to be a spanning set. Okay. If alpha k not equal to 0, then Wk can be expressed as 1 by alpha k V1 minus alpha 1 by W1 alpha 1 by alpha k W1 plus alpha 2 by alpha k plus etc. plus alpha k minus 1 by alpha k, wk minus 1 wk minus 1 plus alpha k plus 1 divided by alpha k. We've just taken wk to the other side. So we don't have coefficient of wk. Wk k plus 1 is there. Plus etc. Plus alpha m by alpha k wm. So what does this say? We have how many vectors here? We have k minus 1 vectors here. We have m minus 1 vectors here. We have another vector here. So these are w1, w2, etc. up to wk minus 1, wk plus 1, etc. wm. We have another vector v1. So this is basically a linear combination of vectors w1, w2, etc. wk minus 1, v1, wk plus 1, etc. wm. Okay, so this is still uh, uh so yeah, so we can replace wk by v1 and still and but the is enough. Moreover, w1, w2, etc. wk plus 1, v1, sorry, k minus 1, k plus 1, etc. wm is linearly independent also. How do you prove this? Assume they are not linearly independent. And again, uh, show this by contradiction. How do we show this? Okay. This is something which we have to think about. We'll come back to this. Show this. Proceeding this way, we can replace one of wi by v2 and again another wi by v3, then v3, etc. vn. However, unless m is equal to n, there will be some vectors w left over, but any leftover wi can be expressed as a linear combination of set of vi's. What does that mean? Wi's, the leftover wi are wi's are linearly dependent on vi. But if that happens, then what do I do? The setup can no longer, it's not just a set of wi, the set of vi and the set of leftover wi's can no longer be a basis. This contradicts the definition of basis because basis has to be linearly dependent. So M should be equal to N. Otherwise, it's a contradiction. So if two bases span vector space, then the number of elements in both the bases should be equal, or the dimension of vector space is always unique for a finite dimension vector space. This is actually what is known as the basis theorem. Okay, there's some point we have to prove here still. So whenever we are replacing a vector, I mean, the set of WNs by Vn, still linearly independent. We'll prove that in the next session. We'll start it by the next, and we'll move forward. Let's end the session here.